Good morning, everyone. Welcome to science. Well, here you go. Here is our question of the day. The main topic of what we want to get to today is going to be talking about something called buoyant force. Right? Buoyant force is this force that happens to anything that's submerged under the water. And you've experienced this because if you've ever been to a pool, and let's say you're with your friends before social distancing, and you kind of grab them, and do you ever like experience this where you grab your friends and you can kind of throw them around in the pool and everything like that? Well, did you ever think if you tried to do that on land, it would be super hard? You're not like, unbelievably superhero kind of strength or anything like that, so you can't do that, right? And so that's what we call buoyant force, right? It's this force that's measurable of things that are submerged under the water. The water literally is pushing up on those objects. So something like today in our question of the day picture right here, like this boat, right? It's underneath the water, so there's some buoyant force that's being applied to it, right? And so it just literally makes anything that's underwater feel lighter. Let's say if you take a brick, right? You can lift up a brick and it's heavy, but if you put it underwater and try to lift it up, it's noticeably lighter. Now, not that it doesn't weigh anything or it's unbelievably light, but it's definitely a little bit lighter. And you can actually measure this force for it. Okay, normally in class, we would be starting to build our water bottle rockets really soon. And I would tell you to have these materials. Instead, what we're going to do is this week, I'll build one and show you, how it's done and everything like that. So you don't have to worry about that. Also coming up this week is going to be, yes, Mentos and Diet Coke, right? There's two great tastes that taste great together. And we'll see that, also has to do with pressure and everything for us. But for today, what we want to get to today, the main event is buoyancy. Right? Buoyancy is this force that gives things the ability to float. Right? So today we're going to talk about things floating and sinking. And two examples that I can give you are, let's say, a boat or a rubber ducky right here. Right? A boat or a rubber ducky floating. Or the other big example could be an iceberg. Wait, where'd my iceberg go? Hold on, there we go. Iceberg. Let me show you an example about these two things. All right, everyone. So I'm talking about floating and sinking here. And I've got my cup of ocean for us, would be one example. And here is the boat, right? So you'll love my plastic boat and everything. Now, if you put the boat in the ocean, amazingly enough, the boat floats, right? So this is what buoyancy is talking about. In fact, I can even add some weight into the boat and push down on it. And you can see as I push down, the water rises because the volume that the boat takes up is being, taken up by the volume of the water. The boat will keep floating as long as the volume of the water is more than the volume of the boat, right? And so that's what's going to keep that floating, right? The water is pushing up on the boat. So yes, the boat has mass, it has weight, it's pushing down, but the water is greater, so it's pushing up, and that's hence where it floats. Now, closely related to this could be another phenomenon also happening in the ocean would be the iceberg. Yes, you love my iceberg. It's massive, right? Ice obviously floats. Everyone knows that. But did you notice it just barely floats, right? That's what a lot of people don't notice. So if I put the ice in, sure enough, it's floating. But this is where you get into that iceberg effect, right? Ice, it floats, but just barely. So if you're seeing an iceberg, and you can see it right over here, right? The iceberg is kind of like floating on top of the water right there, right? That's my iceberg. Let me see if I can get this even bigger. Maybe. There we go. There you go. You can see the top of the iceberg right there, right? That's where the term tip of the iceberg comes from, right? If you're out in the ocean and you see an iceberg, hence, my little chunk right there, right? That little iceberg floating above the water. Well, it's just the tip of the iceberg. Look, the iceberg is much, much bigger below the water. And so that's where, there we go. That's the perfect shot right there, right? That's where the term comes from, tip of the iceberg, right? There's way more below it because while the ice freezes and it traps air into the water that freezes, right? You can kind of see some of those little bubbles in the ice cube, right? It just barely freezes because it's still water. It's still the same density as the water that's around it. It's got a couple little pieces of trapped air in there, and that's why it's just barely floating, right? So that's another great example of buoyancy. And this one's nice because you can drink it too. Right, and so there's a great example right there of floating and sinking, talking about boats and icebergs. Right, another cool example could be this right here.
Three spacewalkers
right,
involved
this,
in
let me
activities.
try to turn this down a bit. This right here, this is one of the largest indoor pools in the entire world. It's actually owned by NASA, right? And the pool, what makes it one of the biggest, at least by volume, pools in the world is because it's very, very deep, right? And what they do is it's made to be really big so NASA can take mock-ups of giant chunks of the International Space Station, or back when they had the space shuttles, they could put mock-ups of the space shuttle in the water. And then it's the best way that astronauts have of actually practicing, spacewalks and moving around in space and fixing things and everything. So when the astronauts do this, when they practice their spacewalks here on Earth, they actually wear the exact same spacesuit that they wear out in space, right? So just like it protects them from the vacuum of space, it protects them from, getting wet in the water and everything too, right? Because it's naturally got to be airtight. So they will actually wear their custom spacesuit down there in the water in the tanks, and they'll actually repair, mock-up satellites or, do routine maintenance or things like that. And they'll do this many, many times down here on Earth practicing before they'll go up into space and actually try doing it, right? So it's kind of a cool example of, things floating and sinking. Really, one of the only differences is if you look on their feet right here, the astronauts are going to have weights attached to their feet so that they makes them kind of what's called neutrally buoyant. They don't really float, they don't really sink, they're kind of like right in the middle. And then you can see here on Earth, obviously, they've got scuba divers around them just for safety reasons and everything, right? So it's a great example of floating and sinking things, right? So this idea of things floating, that's what's called buoyant force. It's this force that pushes up on objects, helping them to be able to float. And that's why, let's say, a giant cruise ship, which you probably don't want to go on right now, but when things get back to normal, cruise ships are fun and everything, right? Do you ever think about it? I mean, how does that float? I mean, you've got all these, like, look at all these floors of steel and cement and rocks and tiles and food and people and, I mean, all kinds of crazy stuff. How is that floating way up in the air, right? It's because the ocean, think about the ocean, is unbelievably more massive than this little tiny boat right here, as big as this boat is. So you can even have, like acrobat trampolines and I don't know what's going on in this boat and everything, and it still floats, right? Because of that force.
We need to play the game of Will It Float? All right, so your mini lab activity today could be this, with your family's permission, to determine will it float. So we'll start off with something easy. I've got a plastic baggie filled with air. What do you think? Will it float?
Yeah.
Okay. Well, yeah, it floats easily, right? Because obviously it's less dense than the water. This is just filled up with air. So that's kind of an easy one and everything, right? So let's kind of move on to something else here. How about duck sauce? Duck sauce, will it float? What do you think,
full.
Josiah? Yeah, it's not 100% full. If
But
it's all right, so put it in there gently. What do you think? Oh, that's sank. And
let's hope there's not
It's a good thing that there wasn't a tadpole under there. All right, so duck sauce definitely sinks and everything. Closely related. Oh, I don't know. The jam. What do you think?
It's gonna sink.
Let's go sink. Put it in gently, maybe. Oh yeah, that's not even close. That's not even close. Oh my goodness, they're gonna have some jam in there if you're not careful. Okay, let's try something. Oh, how about this one? Yogurt. Now yogurt, will it float? Will it float? Yogurt floats! Ding 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 ding! Oh, we should have the bell. Do we have a bell? I don't remember where our little bell went.
It's in your room.
Is it up here?
It's up in the lab, but yes. It's up in the lab desk at your lab desk.
Ah, okay. Next thing, peanut butter.
Oh, a tadpole.
You're petting the tadpoles. Here we go. Peanut butter. Will it float? It's not full.
It's definitely not full, but
Okay, what do you think?
I think it. Well.
Yes, peanut butter floats. Ding. Let's try tuna fish. Will it float?
Oh.
It sinks, but it was fighting for it. It didn't sink as bad as like some of the other stuff there, actually.
All
Right.
right.
Oh, yeah, the tuna fish, actually, because of the shape of the can, Josiah's kind of figuring this out, you can actually try to capture a little bit of air in there. And so it does, like, right at the very beginning, want to float for just, like, half a little second there and everything because of that. Let's try a banana! What do you think? Will do bananas float? Who knows? But now we will. Banana floats? Yes! Ding, 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 ding! Bananas float, believe it or not. Closely
Nice.
related to the banana. And our last contestant of the day is the mighty orange. Now, what do you think? Float or not float? What's your hypothesis? It floats! It floats! Yes, the orange floats.
Now, here's the way buoyant force acts. Doesn't matter what the object is. I don't know why I picked Lego Chewbacca, but I did. Right? Let's say you have Lego Chewbacca and Lego Chewbacca's under the water, right? Sure, there's a matter of there's some force pushing down, right? Gravity's still pushing down on Lego Chewbacca, but the further down you go, the more water molecules are pushing on him, right? So yes, there's a little bit of force from the water pushing down here, but there's force pushing on Lego Chewbacca from the sides, right? And the further down you go, right, there's less pressure on his head, more pressure on his feet. And then because all this water is down below, that's where the greatest pressure is, right? There's more pressure pushing on the very bottom of Lego Chewbacca's feet, more pressure on his head. So that's what's causing that buoyant force, right? It's the weight, right? You've got all the mass of all these water molecules, plus these, plus the layer of this water molecule, plus these, and there's just billions and billions of layers of water molecules, and that mass adds up, right? That's pressure that we were talking about last week, right? There's more and more pressure the further down you go on Lego Chewbacca, and the net result is towards the bottom of him, in this case, there's more pressure. There's more water molecules pushing on his feet because you've got these water molecules plus all the ones above it than you do on his head, right? And that is buoyant force, right? Density is the other thing that's going on here that makes things float or sink, right? Density is just the ratio of how tightly packed the molecules are in a particular substance compared to the density of the liquid, right? And so the density of liquids can change, right? If you've got does anyone know, oops, all on here, this picture right here, I've got someone floating in the ocean, but the water right here is full of salt, right? This is actually a picture from the Dead Sea because the water is unbelievably dense because the water molecules, right, are packed in there with tons and tons of little salt molecules are in between the water molecules. It literally means this water is more dense, right? If you're in a boat and the boat's floating, wait, where's my boat right here? Right, if you have the boat floating, right, on ocean water, the boat will float higher, right, because the water is more dense and it pushes up, right, it's pushing up on the boat more. If you go into fresh water, boats will actually sink down a little bit deeper into fresh water simply because the water's not as dense, right? And so, ocean water floats a little higher, fresh water sinks a little bit lower. And you can imagine, if you're the captain of a boat, you've got to pay attention to this, right? You don't want to be in a situation where you load up the boat to its complete max fullness and everything in the ocean, then take it, like, say, into one of the Great Lakes where the water's not as dense. The boat's going to sink down deeper. Let me show you, we'll cut to the video right here. We have my piece of Brazilian hardwood versus Dwayne the Rock.
Hey everyone, and welcome to the Science Kitchen Laboratory. So today we're talking about things floating and sinking, or buoyancy, and we're going to use the tadpoles as our example for today. So to start off with, we have two commonplace objects, right? I've got a piece of wood and I've got a rock. And the question is, which one will float? So Josiah, my trusty assistant, what do you think? Will rocks float? Here, come on over on this side so they can see you looking at it. He's coming over here. He's working his way around. So can you first confirm to everybody, because normally I pass this around in class, like, it is a rock, right?
It's a rock.
It's a rock. What do you think? Is it going to float?
Looks like it might have some holes.
It definitely has some holes in it, yes.
It's kind of weird.
It's kind of weird. So what happens if you put it in with the tadpoles? Oh my goodness, it's a floating rock. It's complete madness in the world. You know why it floats?
Because there's holes in it.
Yeah, there's holes in it. Now this rock right here, I aptly named this rock the Rock. Get it? Now this rock right here, it's a specific kind of rock. It's not just any ordinary rock that you'd find in your backyard, at least not in your backyard here in Pennsylvania. This rock is pumice, right? And so pumice is lava that was, well, it was lava when it was underneath the earth. Well, I guess it was magma when it was underneath the earth, if you remember from last year. But once it shot out of the volcano or oozed out of the volcano and it becomes lava on the surface, it's really, really hot, right? Can you imagine, you know, magma turning into lava is really hot, right? But what happens is, with pumice, it cools off in the air, right? It cools off so fast, in fact, that kind of like an ice cube, it traps millions and millions of little tiny air molecules in there. And so it's very, very light, because it's kind of like hollow, but hollow everywhere. There's millions and millions of tiny little air bubbles trapped inside the rock, so many that the rock actually floats. Now, if we do its arch nemesis, the wood, here you go. Now confirm again, Josiah. Again, I would pass this around in class normally. It's a piece of wood, right?
It's a little heavy for wood.
It is heavy, right?
It's
so
like maybe 2 pounds?
Yeah, maybe. So what do you think?
I think it would sink.
You think? So put it in there. Let's see what happens to the piece of wood. It sinks like a rock. Get it? Rock. Yeah, now the thing with this is the most dense wood on Earth, right? It's a type of Brazilian hardwood, and the little tiny, if you figure, you know, the fibers that are inside the wood, they're packed super tightly together. So tight that it's very, very dense. So dense that it actually sinks in the water, right? So that Brazilian hardwood, it's so dense it actually sinks, whereas the pumice is so undense that it actually floats here with, you know, the little tadpoles that are going around with it. Brazilian hardwood, it's very expensive because it's so dense, but if you're looking to make something really, really strong, let's say like a hardwood floor, Brazilian hardwood you could actually make, that's a choice, you can make your floor out of that, and then it won't scuff and chip and get scratched up and everything like that, like some of the other things.
All right, so when we're talking about buoyant force, a buoyant force is this upward force that acts on that fluids have when they exert it on an object that's sunk below the water. Doesn't matter what the object is, whether it's a little tiny fish, like in my picture right here, yeah, that cute little fish, or if it's the surfboard, right? Part of the surfboard that's in the water, right? That water is pushing up on it, and that's what's holding that surfboard up, right? This is what's known as buoyancy, right? So this is the phenomenon known as buoyancy. That buoyant force, it's equal to the weight of the fluid that's being displaced by the object. So let's say in the case of this submarine right here, right? You've got to think the submarine is floating in the water, but it's because it's displacing or it's pushing away that much, you know, whatever the weight or the mass of that entire submarine right here is, right? It's being pushed away by, you know, it's pushing away that much in the water. And because there's way, way more mass in the ocean right here, that's what's pushing the submarine up. Right, if you try to take this submarine and float it, let's say in a bathtub, it's not going to work because there's not nearly as much mass in the bathtub water as there would be, you know, for the entire submarine right there. Right, so that buoyant force, that's what's determining, right? You know, the size of that buoyant force is determining whether the object's going to sink or float. Right, and so now is where we can play the sink or float game. Will it sink or will it float? Anyway, that was fun. Let me show you this super short video, all right, and we'll get to submarines, how they work, floating and sinking and everything, which is cool for me because my father, he used to be in the Navy and he worked on a submarine, so he liked to explain this too. But here's my kind of little mock-up of this.
About midship, with the U-shaped ballast tanks around the inner pressure hull.
All right, so inside the submarine, there's what's called ballast tanks. They're basically open cylinder, or well, they're basically chambers inside the submarine where water or air can be in. Right now, it's filled up with air, so it means the density is high. Well, density is low of the overall submarine. When they fill it up with water, the density gets really high and it goes down under the water.
The tank vents are closed, and compressed air is let in at the top. This forces the water out and lightens the submarine so that it surfaces.
There you go. So that's what's going on with submarines. Let me show you the Cumberland Valley submarine.
Let's get to the Cumberland Valley submarine. You didn't even know that we had this in the budget, but yes, there is a Cumberland Valley submarine right here. And what we need to do is we want to get the submarine to work just like a regular submarine, right? And so to do that, the way that submarines work is, now think about it, just like we've been talking about. Submarines are made out of metal, right? But the submarine that's made out of metal, it can obviously rise and sink in the ocean and everything. The way they do that is because of the buoyancy, how dense that actual submarine is compared to the water that's around it. So what you have to do to get this to work is we first have to fill the submarine up with some water here and everything. Right now the submarine's kind of like hanging out on the bottom down there, it looks like. If all of a sudden you're in your submarine and you decide, oh, we need to surface, Captain, then what the captain does is they pump air into, in our case, this green ballast tank, and if you watch the air level, when Josiah pushes the lever, go ahead, the air goes up, and then the submarine goes up. It surfaces. You know, they can look around. If they're like, oh my goodness, bad guys, dive, dive. Whoop, 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 whoop. Well, he lets the water come out, and there you go. Perfect. Yep, there you go. It's all good. Now the submarine can go back down to the bottom.
And we trapped a lot of...
Right, so yeah, and then if they want to go back up, then we just have to restart the whole process again and pump more air back in.
So, an object floats when it displaces an amount of fluid whose weight is less than or equal to its own, right? So the water's changing the density of the overall ship that's floating or sinking, in this case, a submarine that we have for it, right? This works for really giant submarines. It works for little tiny ones, right? If the density of the object is less than the fluid around it, it's going to float, right? So that's like taking a submarine and adding air to it, right? If the density of the object is more than the water, then it's going to sink. So that's where you take, the submarine, add some water into it, right? So now you've got water that's pretty much the density of the water around it, plus all the metal and glass and stuff that's inside the submarine. That's going to make it want to sink down, right? Because now its density is more. This is the way that fish work, right? A fish swimming around, let's say if there's a fish kind of like our middle fish right here swimming around, that fish, if it's not going up or down, it's got a little swim bladder in there. It's just like the exact same thing as the ballast tanks inside a submarine. If it's not really full but not really empty, the fish just keeps swim this way or that way, right? If the fish decides, oh, I want to go up, right? It takes in some oxygen through its gills, it pumps air into that swim bladder, which gets big, and then the fish goes up, right? If the fish decides, oh, there's some food down below, right? It literally uses its muscles, squeeze the, that little tiny bladder, that swim bladder, makes it small, and then it goes back down. Does this sound familiar to you? We talked about that last week with this guy right here, right? Remember the Cartesian diver? Right now, there's a pretty good amount of air inside of that tiny little eyedropper that's right here. But if I add some pressure in, right? What happens is I squeeze and add pressure, and that squeezes the more water up into the eyedropper right there. It means less air is inside of it, and it's exactly like the fish now, right? Less air inside the eyedropper, and the fish goes down, yay, right? If the fish decides like, oh, there's some food at the top, I see, right? It basically lets more air in, and it goes up, right? So that's floating and sinking right there. That's buoyancy, right, for it. Now, if you, just in case you want to know, right, what's the density of water? It's 1 gram per cubic centimeter, right? Or 1 milliliter is, the common way that we talk about it in science, right? So that's the density of water. 1 gram per cubic centimeter is going to be it. So for today, check out the folder. Make sure you watch, this video, obviously. There's going to be our short reading section, and then you're going to need the quiz.